Hey everybody, it's Ben Manning for our next edition of Data Science Lab. Just wanted to do a quick reminder right quick to visit HashMap's blog at hashmapinc.com/blog. We update our blog just about every week now, and there's some really good information on here. You can see the newest article is an article on all clear for IoT-based railway analytics. Really cool stuff by Venkat Sekar. And I've got a couple articles on here myself, but we're really proud of this blog, and we're trying to grow it as much as we can. So feel free to subscribe and keep an eye out for our latest updates. Some other useful information that we're going to be going through today, and I'll post these links in the actual summary information of the video. We're going to be talking about tidyverse.org. These are R packages for data science. We're going to be talking about Plotly, which is a really good open source graphing library for R. And from time to time, we might reference the R graph gallery. So those are three different links that you can add to your, four different links actually, that you can add to your library. So just a quick summary of where we left off in our last video in this Intro to ML series. We went over sort of R and R Studio. We imported the Iris dataset and we sort of left it there. I think we talked about summary and we talked about structure in the last video. So what we're going to do now is really pick up from there. So that covers sort of very general concepts that are centered around data ingestion, getting data into R, from a CSV file. Now we're going to move sort of to the second and really third steps in the data science process. The first one being pre-processing, and then the second one being exploratory data analytics. We'll do a lot more of the latter than we will the former. So where we left off in the last video was really looking at the structure and the descriptive statistics of our Iris dataset. And we talked about using structure to actually check the data types. And you can see the data types of every variable are listed here. We've got number for sepal length, number for width of sepal, number for petal length, number for petal width, and then species. The Iris species actually came in as a character. And because eventually we're going to turn this into a machine learning classification problem, that's actually the first thing we're going to change. Any of you that have read anything about machine learning, supervised machine learning especially, falls into two different categories: regression problems that deal with dependent variables that are numeric, and classification problems that use dependent variables that are categorical or nominal. Neither of which exist in that state inside of R. Nominal variables or categorical variables are called factors in R. So that's one of the very first things that we're actually going to do to this data is actually change the species variable, which is our dependent variable, from a character data type over to a factor, so it's representative of the nominal data or the categorical data that we need. So we'll do that in just a minute. We're also going to dive into sort of the descriptive statistics that are centered around especially our features, right? Our four different features that are in our feature space, or our four different independent variables. We want to check the different descriptive statistics there. Then we'll dive into to a little bit deeper analysis when we get into EDA, and we'll start plotting a lot of this information. But for now, let's dive into very light pre-processing. We don't have any missing data in this file whatsoever, thank goodness, or we'd be doing a lot of pre-processing. We also don't have any dirty data to clean in this particular file, and that's really good because pre-processing really is centered around cleaning your data, removing any unwanted or unusable data types or symbols that's in your data, and cleaning up any missing values, especially centered around empty values altogether. So since we don't have a lot of that to do, really what we need to do here is the only thing we have to do in pre-processing is change over this species data type. So actually what I'm going to use is as factor to do that. There's a really great function in R called as dot, and you'll see this a lot in many of the tutorials online. And what I'm going to do is use as dot factor to actually convert what the existing data type of species is over to a factor, which is also, like I said, nominal. And I'm just going to overwrite it. So I'm going to use iris $species. That is the actual column that contains that data. And I'm going to assign it to as.factor here. You can see there are a lot of as dots, right? As.dataframe character, as.dataframe complex, as.list, as.vector. If you want to move one data type to another or typecast like you would in traditional programming languages, this is how you do it. And since I'm going to as.factor here, I'm also going to just reference species again. And you can see now if I run a structure on this, now species is a factor with 3 different levels. So essentially I've changed species from a character or a string, if you were thinking about something like Python or JavaScript or any of those, to actually a multi-class variable. So now I'm preparing this for a machine learning problem, right? So that's really the only pre-processing that I have to do here. I'm good. I'm ready to go. These other 4 need to be numeric for the classification problem to work, and they're numeric anyway. So I'm going to leave them in that format. And now I've got a nice factor here with 3 different levels of classes. So I'm ready to rock. So really the next thing we want to do is dive into the descriptive statistics. And I already showed you that in summary, right? If we look at the summary of IRIS now, we've got the 4 numeric features and the 1 categorical variable at the end. And you can see R does a really good job of knocking out sort of what the descriptive statistics are around each one of these. You can see the mins for sepal length and sepal width are very similar. The mins for petal length and petal width are not similar, right? The mins for petal width are actually down to the tenth, where the smallest length that we have is about 1, right? So you need to kind of take note of that. That difference in scale might actually be problematic. We go ahead and look at the maximums for each of these, and they're generally about I wouldn't say about the same, but they're not extremely variable, right? So I don't think anything's going to cause us a problem with differences in scale on any type of situation where we need to normalize any of this data. So I think we're good to go there. So our next step in this process is actually plotting this stuff. So now that we've sort of seen what the numbers look like, let's actually visualize what the data looks like. And we're going to do this in a couple of different ways. So traditionally, most of your die-hard veteran R users use ggplot2 for most of their plotting needs. It's fantastic, been around forever, is a cornerstone of most visualization in R. I like to use Plotly just because Plotly is coming on very strong. I like the API that the Plotly folks have worked out for beginners in R. It's much easier to understand. And almost everything that you do in Plotly inside of R, you can also push to the cloud, including fully interactive charts. So that's very, very strong, right? I don't have to go out and build a shiny application or something like that to make something real time like I would have to with ggplot2. I can push everything that I do in Plotly right to my account, my Plotly account in the cloud. So I'm not going to be doing any of that today, but I wanted to let you know that I would be using Plotly for most of this stuff. So I've already installed Plotly. So I'm just going to go ahead and call the library here. So we can do some cool things. So the first thing I want to do is some bivariate analysis. I want to look at the relationship between sepal length and sepal width. Now we'll get down to some specific statistics, things like correlation, closer to the end of this video after we do visualization. But I want to get us into visualization first where we can actually see what these things look like. You can see Plotly has just its own function built in. This is really simple. If you've ever used ggplot2, you'll fall in love with Plotly because it's a lot simpler to use. It's just asking me for the name of my data frame, and then what's my X, and then what's my Y. Because this is bivariate, obviously, we're going to get some type of a comparison. We'll get one variable in the X and one variable in the Y. Now, you can see this shows up over here in the viewer, and obviously we can zoom in on this a little bit if we'd like to. You can see here we've got sort of one cluster of data, and then down here at the bottom we've got sort of another cluster of data. If I was to build a machine learning algorithm, right, with something like or use a machine learning algorithm with something like SVM, notice this linear separation here is very, very easy. If I wanted to separate these two, build a classifier that separated these two things from one another, it'd be very easy to do. In general, you see that there's, you do have sort of this somewhat linear positive correlation between these two because they are increasing. I don't want to say at the same rate, but they are increasing linearly. One is much more broadly distributed than the other. So, that's a really good way to take a look at bivariate comparison between those two. What if we wanted to go a little bit deeper with Plotly? Something I like to do, since we have multi-class information here, that's really what our dependent variable is, right? Is the species. So I like to build the exact same plot, and I like to use species as the actual color to break these things up. And if I break this out into the viewer, you can see this overlap exists now, right, between versicolor iris flowers and virginica iris flowers. You can see there's an overlap between their sepal length and their petal width, but not down here of the sort of first iris flower, which is setosa. It's kind of sitting out here on its own. So that can pretty much tell you that this iris flower is a smaller flower than the other two altogether, and the other two, versicolor and virginica, are somewhat similar, or at least have somewhat similar characteristics right here where they overlap. But I really like that characteristic, that this type of plot in Plotly, and it's super simple to do in comparison with something like ggplot2. So that's really all we need to do on our scatter plots. We've got enough information there to know what we need to do as far as a machine learning algorithm. We know that we don't have tremendous outliers in data. We're going to look at that here in just a minute, get a little bit deeper with that. But things aren't off the chart, and that's really what we're looking for in EDA. We're trying to get sort of some knowledge around what we're trying to do and what we're trying to deal with as far as data is concerned. I'm not a botanist. I don't have a background in anything to do with plants, right? I'm an engineer. So I'm trying to get a better understanding about the type of data that I'm dealing with and see if I need to modify anything in any way. So speaking of that, one of the sort of the mainstays of exploratory data analytics when it comes to machine learning is really looking for outliers. And the best way, obviously, to identify outliers outside of your descriptive statistics is really the traditional box plot. Plotly has a great API call for box plots, and it'll actually stack them in as many as you'd like, one at a time. And we can see that when comparing our sepal length to our sepal width, which is the orange one here, actually does have a handful of outliers. Nothing to worry about, but if I had 1 million data points here, this scale might be something to worry about. Building machine learning algorithm to solve this type of problem, that would be something that I need to take into consideration. Do I want to leave those outliers in the problem, or are they important enough to model, or do I clip those out and just work with the quartiles within the data? So let's do one more of these in Plotly. By the way, I'm just pulling this information, this Plotly information, right out of the Plotly reference that I showed you right at the beginning of the video. This is nothing custom that I'm writing. Again, just comparing the other two, petal length to petal width, nothing as far as outliers are concerned. You can see that that sort of the middle of the data is somewhat skewed a little bit to the right here and a little bit to the right here, and that verifies what we saw earlier when we did the overlapping scatter plots. What about the species, right? So we need to kind of plot that. We're not going to do that in a box plot, right? So that's a nominal variable, so we can always grab our favorite histogram to kind of see where those things line up. And since we've already converted those to multi-class data, we can easily see, and this is extremely valuable for a classification problem, we can easily see that we have an equal distribution of each one of these flowers across the entire data set, right? That is very important when it comes to multi-class classification, because you don't want an unbiased data set, right? Or a biased data set, depending on which way you look at it. If you're doing something like fraud detection, right? Maybe you have 1 million observations and 999,000 of them are considered okay, not fraudulent, right? What's left over, the very, very, very small percentage, might be considered fraudulent. That's an unbalanced data set, and what happens, what problem that creates is when you're using classification algorithms or classification problems in machine learning, is generally they will respond to that type of data like everything is fine in your model. You'll have a high accuracy if you're using just accuracy, which is probably a mistake there to begin with. But for newbies, if you're using just accuracy, you may get a very high accuracy when in reality your model is really just training on what it sees as being correct, right? Because accuracy is sort of the accurate classifications over the total number of observations, when you should be using something else like sensitivity or precision or something like that, where you're really diving into unbalanced classes. So anyway, that's for another lecture. So it's a good thing we've got an equal number of classes in each one of these. So that's scatter plots, that's box plots, that's quick histograms for EDA. I don't see anything to really worry about in any of this data, and that's a good thing, right? That's part of my knowledge discovery in exploratory data analytics. Obviously, this is a tiny data set, and when we do deep dives in exploratory data analytics, we're normally building on things like normalization and standardization, right, and centering data and all these other things that we would probably be doing in pre-processing. We don't have to do that here, obviously, because it's a really small data set. It's a simple data set and a clean data set to begin with, and it's right for this type of video. Look for future videos that do deal with much more complex data. This is really centered around an introductory series. So last but not least, we want to look at correlation. And correlation is not something that you would generally dive really, really deep into in a classification problem, much more so a regression problem where collinearity and things like that could cause overfitting. But it's worthwhile to do this exercise when we're talking about exploratory data analytics anyway. So we're going to go ahead and do it here. And I'm going to use just Pearson correlation to actually do this. So to do that, you can just actually use the COR function. And let's go over here, make sure we're loaded up. Yep, we're good to go. And let me bring it in. I'll show you what it looks like. So just a simple core, passing the data frame here, and then the method is Pearson, right? So I might get an error when I do this, so let's look and see. So it says error in core, error in that actual function. X must be numeric. So what that means is, right, if you go back and you look at the standard definition of correlation, what you're talking about here is the strength of relationships between two or more numeric variables. In this case, remember, we converted species from a string to a factor. So species is not a number, and that's why I'm actually getting this error. So in order for me to actually build a correlation matrix, I'm going to have to strip out the feature space and just look at the 4 independent variables on their own. Okay, now there are a lot of different ways we can do this. What I like to do is make my own data frame that contains just the feature space, because during EDA, that's really what you're looking at anyway, right? You are still looking at a relationship between individual features and the dependent variable, but the next step in the data science process after this is feature selection or feature engineering. So let's go ahead and strip out the features, the potential features, and let's see if we can actually build this correlation together. So I left a link in the comments, or in the in the video for Tidyverse, and I showed you we'd be using that up front. The library is loaded, and one of the actual functions we're going to use out of Tidyverse comes from another package called tidyr, and it's called select. And really all this says is I want to make a brand new data frame named iris nums. I want to use the original data, which is iris. This is a piping function, right, that assigns the left to the right in this case. And I want to use, hang on just a second. I want to use the select function. I want to select columns 1 through 4. That's what that actually means here. So if I go here now and I type iris nums, you can see it's only referring to sepal length, sepal width, petal length, and petal width. So now if I turn around and I go back to my actual core and do iris nums instead, I get correlation coefficient values using Pearson correlation coefficient for the strength of relationship between each one of these variables. If this was a regression problem, I'm really looking for highly related independent variables, right? You get something like this 0.81 here or this 0.96. These are two different variables, right? You have to be careful of that when you're doing regression problems, because that relationship can easily bias a machine learning model. We'll talk about that when we get to the regression portion of this series. Right now, all we're worried about is classification, so we're not going to worry too much about that correlation. And by the way, just a quick aside, especially for you newbies out there, it's a common misconception, you'll hear this a lot, that machine learning algorithms need correlation to work, and that's not the case. That's actually a misnomer. If all machine learning algorithms needed correlation to work, we wouldn't really need machine learning algorithms. We just use statistics for everything. So that's the beauty part of many machine learning algorithms, is they will find relationships that exist or patterns that exist in the data, regardless of correlation, which is really, really good. It's what we want. So that's our correlation, right? Those are our correlation coefficient amounts that gauge the relationships. Obviously, this falls between 0 and 1. 1 being highly related. You see the ones on here, but this is just the intersection of the same exact variable. So disregard the ones here. So last but not least, this is kind of where we need to leave off EDA, because we don't have a large data set. Generally, I like to understand sort of the statistical significance or the significance levels in all of this type of data, and we're going to leave it with the numeric variables for now, right? But this is generally referred to as a p-value, and in statistics and things like t-tests, you can go back and you look at a p-value, and there's a certain threshold or a cutoff for the p-value between any two given numeric variables that represents they are statistically significant, and their relationship is much more than just random, right? So there's a package in a statistics package inside of R called HMIS, HMISC, and I think I already actually have it installed here. Let's look and see. HMIS, that's what it looks like right there. HMIS actually has something called R-core. R-C-O-R-R. You see it right there. If you use R-core instead of just regular correlation like we used previously, you're gonna get your correlation coefficient just like you did prior, but you're also going to get associated p-values, which is extremely important, because if you have any relationships that exist that you think might be worth noting, you can go back and look at their p-values. If you have low p-values, super low p-values, I think it's 0.005, that you're looking for as a cutoff, then you know that that relationship is there more than just randomness, right? There's some statistical significance that actually deserves further study between these two variables, whether it being independent and dependent, which is most often studied, or even two independent variables. So R-core just uses the same iris nums data frame that I've used, but I'm passing it as a matrix here. So we actually do get some calculation. You can see these are rounded off, by the way, rounded off correlation coefficient values. Number of observations is 150, and here are your p-values. So the p-value of sepal length to sepal width is 0.1828, not very high. See all these others that are 0.000, right? R is just rounding those things off because they're super low p-values anyway. So, you know, that's sort of the proof we need at the end of this. If we were doing a t-test with multiple variables, this is kind of the proof we need at the end of this, that these are statistically significant. So where do we go from here? That's kind of the end of EDA, and we're kind of at the end of our time here, right? We could make a correlation plot if we wanted to build a heat map of this. Maybe we've got 20, 30, 40, 50 variables, and we want to actually visually look at this, or we want to present this to an investor or our boss or our manager, and we want to have some definite justification in a visual way of what features we're removing and which ones we're keeping. We could certainly build a correlation matrix with a heat map if we wanted to, using another package called CorePlot. Outside of that, this is a simple data set. Our next actual series, our next video in this series, if we were dealing with complex data or more complex data than this, would be feature selection. We've already done that, right? We only really have 4 features, and we're going to leave them all in the model. So our next video that will be coming up real soon will actually bring us into the machine learning process, and for that we'll be using the Carrot package. So we'll build 3 different types of models with the Carrot package, all of them centered around classification. We'll do some automated grid searching. We'll do some manual grid specification and do some tuning of our own hyperparameters in every single algorithm that we use. All that's coming up in our next video. So be sure to hit the subscribe button on our channel so you can be notified when we post that, and should be coming up in the next week or 2. So hopefully you enjoyed this. I really enjoyed creating it, and let us know some feedback down in the comments. We always love to hear your feedback so we can continuously improve these videos. Have a great day, everyone.